This is Elohe Amini. We are reviewing chapter 7, range equation, all true quiz and questions, and with working deeply, we are going to be ready for this chapter. I think through these questions, you can be ready 100% for the SPI for this chapter. Which one, it means which choices, is not related to others? A, time of flight. B, go return time. C, round trip time. D, all choices are the time to and from the transducer and reflector. Please pause and think about that, please. So all of them are the same. Time of flight, or the pulse goes from transducer to the tissue, or to the depth that we are determining, and return to the transducer again. It's called time of flight, go return time, round trip time. All the time for going and coming back to the transducer, the pulse from the reflector to the transducer are the same. The average speed of the sound in the soft tissue are, that's true, 1.54 kilometer per second is the same as 1.54 millimeter per microsecond, or 1,540 meter per second. All of them the same. If you want, I can explain to you why. The time of flight and distance that sound travels in the body are, okay, the time of flight and distance that sound travels in the body are directly related. When time of flight is known, we, which one? The distance that sound wave travels. Can we determine that or no? Yes, we can determine when we have the time of flight. For example, we know that it is 13 microseconds. So, and we know the tissue. For example, this is soft tissue, and the speed or propagation speed of the sound wave or pulse in that soft tissue. When we know that, we can determine the distance, that is all the time 2 times of the depth. So we can determine with one of them, time of flight, we can determine the distance, because it is like the time and this is the distance. Each, how many microsecond? Each microseconds for time of flight, it means round trip, going and coming back of the ultrasound wave, go and come back in the soft tissue to the transducer, means 1 centimeter. Which one is 1 centimeter in the soft tissue? Yes, it is the rule of 13. 13 microseconds is the time of flight for going to the reflector and coming back to the transducer. Is for each centimeter is 13 seconds. We know that in soft tissue, every 1.54 millimeter needs 1 microsecond to pass. It is the speed of sound in the soft tissue. Then for 1 centimeter or 10 millimeter, it is 10 divided 1.54 is 6.5 microsecond for only from the transducer, and the same way to the transducer. So 6.5 plus 6.5 equal 13 microseconds. So we have the sound pulse that is coming 1 centimeter or 10 millimeter here. And because we know that every 1.54 millimeter needs 1 microsecond, for 10 millimeter, it needs 6.5, and 6.5 coming and 6.5 returning, it is 13 microsecond. And also total distance is 1 centimeter plus 1 centimeter. All the time, total distance is twice the depth. So the region of interest is 1 centimeter apart from the transducer, and the total distance that this pulse coming and back, going back to the transducer is 2 centimeter. What is the go back time or time of flight for a reflector in the depth of 2 centimeter? Yes, it is 26. Why? Because it is 2 centimeter depth. We know go back time for 1 centimeter is 13 microseconds. So choice A is for depth 1 centimeter. For the depth of 2 centimeter, twice 13 plus 13. So it is for a reflector position depth of 1 centimeter for transducer, the time of flight is 13 microsecond. For 2 centimeter depth, not total distance, is twice that. So the time needs for a pulse from transducer comes to 2 centimeter depth and coming back, returning to the transducer, is 26 microseconds. So we have here for soft tissue, because we know that it is 1.54 millimeter per microsecond. It is for soft tissue. We have the rule of 13 microseconds. For time of flight or coming and returning or round trip, 13 microsecond in soft tissue is 1 centimeter depth, and total distance 2 centimeter. It is very important. Distance all the time twice the depth. For a reflector position 2 centimeter from the transducer, it takes 26 microseconds that the pulse goes to that depth and coming back. So the depth is 2 centimeter, but the distance is 2 plus 2 centimeter. 2 centimeter depth, 2 centimeter coming back. It is total distance. If the reflector depth is 4 centimeter, it takes 13 times 4. It is 52 microsecond, and total distance 4 centimeter coming to the reflector and 4 centimeter coming back. So it is 8 centimeter. And if a reflector is 10 centimeter, it takes 130 microsecond for that the pulse from the transducer goes to the 10 centimeter and coming back. It takes 130 microsecond, and the total distance is 20 centimeter. Please don't forget, it is for soft tissue with that specific propagation speed, 1.54 millimeter per microsecond. A sound pulse is produced by a transducer and travels in an ultrasound phantom. The pulse travels from the transducer to pin D, reflects off of it and returns to the transducer in 130 seconds, coming and returning. How deep is pin D? Yes, 10 centimeter. Why? Because it is 130 microsecond. So for each centimeter, it goes 13 microsecond. For 10 times of that, so 1 centimeter times 10 is 10 centimeter. This phantom is checking range registration for equally distance objects. For 1 centimeter, 13 microsecond. Then for 130 microsecond, that is 1 centimeter times 10 centimeter. 20 centimeter is total distance. Please don't forget. Other way of solution is that in an ultrasound phantom, the speed of the sound is the same as that in soft tissue, 1.54 millimeter per microsecond. Each 13 microsecond means the reflector is 1 centimeter deep. In 130 microsecond, the reflector pin D is located 10 centimeter from the transducer. It is important. A sound pulse emitted from a transducer travels in an ultrasound phantom, reflects off of pin A, then returns to the transducer in 52 microseconds. How deep is pin A? What is the total distance that the pulse traveled? Yes, it is 4 centimeter. It means we know that 13 times 4 is 52. So for A, it takes 52 microseconds goes to A and come back. So the distance is 13. So the time is 13 times 4. It is 52. For the depth also, it is 1 times 4. So the depth is 4 centimeter and total distance is twice of the depth because it comes 4 centimeter and back 4 centimeter. 4 plus 4 is 8 centimeter. The other explanation is in a 52 microsecond go return time. The pin is 4 centimeter deep in the phantom. The pulse traveled a total distance of 8 centimeter, 4 centimeter into the phantom and 4 centimeter out. Concept, the important lesson is that if we know the speed of sound in soft tissue or any medium, then there exists a fixed, invariable relationship between time of flight and distance. This is how pulse ultrasound systems measure distance in biological media. A sound wave is created by a transducer. The reflect off of an object and return to the transducer. The depth of the reflector is 10 centimeter. The round trip time is 2 seconds. What is the speed of sound in the medium? Yes, it is 10 centimeter. You can imagine that we have transducer here and the object or the reflector is here and it is 10 centimeter. From here to the object is 10 centimeter. Okay, and the time for coming and returning is um, is 2 seconds. The time for coming and return is 2 seconds. We know that speed of sound is the distance divided by time. So it is round trip for 2 seconds, but for 10 centimeter, only one time coming to the this 10 centimeter um, is 10 centimeter per second, because this 2 seconds is coming 1 second and coming back 1 second. Yeah, so 10 centimeter per second. So remember that speed equals distance divided by time. You should know this for your SPI exam, range equation. This question illustrates the concept that speed equals distance divided by time. The total distance traveled is 20 centimeter. The time is 2 seconds. 20 centimeter per 2 seconds, 10 centimeter per second. So we have here again the transducer, and we go to the depth of 10 and then coming back 10. So the total distance is 20 centimeter in 2 seconds. So for only 10 centimeter coming 1 second, so the speed is 10 centimeter per second. The pulse time to a reflector is 52 microseconds in soft tissue. The depth of the reflector is, yes, 8. It is a very tricky question. So it is explaining that if it is transducer, the pulse time, our pulse is here and coming to our object in 52 seconds. So it is only for to the reflector, not coming back. 52 seconds to the reflector. The pulse time to a reflector is 52 seconds. In soft tissue, the depth of the reflector is 8. Please pay attention to the word to the reflector only, not round trip or time of flight. It is just to the approaching to that reflector. So we can say it is to the depth. 6.5 microsecond for 1 centimeter, then for 52 is 8 centimeter, or 1.54 millimeter per 1 microsecond. Then for 52 microsecond means 1.54 times 52 is 18 millimeter or 8 centimeter. So it is a tricky question. Please think about it very carefully. The pulse round time coming and returning to the transducer in soft tissue is determined to be 130 microsecond, 130 microsecond. The depth of the reflector is, it should be easy. Yes, it is 10 centimeter. The units are very important. So here we have for each centimeter we have one. Oh, what happened? For each centimeter in soft tissue we have 13 microsecond flight time, means coming and leaving to the transducer. With 130 microsecond depth 10 centimeter and the total distance 20 centimeter. In go return, not the depth. Depth is half of the total distance. The propagation speed of a material is 2 millimeter per microsecond, so it is not soft tissue. The speed is faster. The pulse round trip time is 200 microsecond. The reflector depth is 200 because for each microsecond 2 millimeter. For 200 microsecond, so it is this one 200, this one 200 millimeter too. The depth is very important. Here we have propagation speed 2 millimeter per microsecond. That is not like soft tissue. That is soft tissue 1.54 per microsecond. Round trip time is 200 microsecond. Then each 1 microsecond, 2 millimeter, 200 microsecond, 400. Please pay attention. So from the transducer to the reflector and coming back, total distance is 400. Yes, because for each microsecond 2 millimeter, for 200 it is 400, but it is total distance, and total distance divided by 2 is the depth. So depth is 200 millimeter or 20 centimeter. The time it takes for an ultrasound pulse to travel 1 centimeter round trip in soft tissue is, yes, it is 13 microsecond. So again, we have soft tissue propagation speed that is 1.54 millimeter per microsecond. For 1 microsecond, 1.54 millimeter. For 10 millimeter, the time is 10 divided by 1.54, it is 6.5 microsecond. And because we have round trip, 6.5 plus 6.5 is 13 microsecond. Please pay attention to this one. For instead of the time for the depth of a specific reflector in our image, the time of a pulse go return from the transducer to the depth of total bottom of that image is, here we have our image depth. For example, we have our image depth that is 5 centimeter at the bottom. Okay. Instead of telling that from transducer to the 2 centimeter, for example, the region of interest or reflector, we say the time for coming the pulse all the way, or our depth total at the bottom of our image and coming back. What is this? It is pulse repetition period all the way. The time for trip, round trip or go return to the bottom of that image is pulse repetition period. So in our total depth of the bottom to the bottom of the image, not to the reflector, total image depth is 1 centimeter. What is pulse repetition period. So the pulse coming to the total depth and coming back, the next one is coming, it is pulse repetition period. The next one is repeating. So here 13 microsecond. PRP equals 13 microsecond per centimeter times image depth. Deeper imaging, please remember total to the bottom of the image, not a specific reflector between the image. For example, total depth is this one. And we are going to, our pulse is coming here and coming back is PRP. And the next, after that, the next one coming, the repeated one. So it is for 1 centimeter, it is 13 microsecond. If we increase the depth with the button of depth, we increase pulse repetition period and decrease pulse repetition frequency. If we determine the numbers of times that the sound pulses go from the transducer and come back in 1 second, not microsecond, it is so per second, that or hertz, what is that? The pulse, not fundamental frequency, the pulse. Yes, it is pulse repetition frequency. So our pulse is coming down and they're coming back. The next one coming. After 1 second, how much, how many times the pulse repeated? It is pulse repetition frequency. This one is a little bit explanation to that. Pulse repetition period is the time for go return of one pulse to the total depth. So this one is not correct. It's not per second. Per second is pulse repetition period because it is about the pulses. Why fundamental frequency is not correct? Because it is not changing with the depth. Fundamental frequency is fundamental frequency. Never we can change it, but we can change the rate of the pulses, pulse repetition frequency, pulse repetition period, with changing the depth. And frame rate is PRF divided by lines per each frame. And it is not about the frame, it is about the pulses per second. If the sound pulse propagation speed in soft tissue is 1540 meters per second, what is the PRF for 1 centimeter depth to the bottom imaging? Yes, 77,000 hertz or 77 kilohertz. The speed of sound is not only for coming down, it is also for coming back to the transducer. So 1540 meters per each second, it is coming down and coming back. So 140 divide by 2 because coming to the end and back to the transducer. So PRF is half of the speed. Here we have a little bit better explanation. So 1540 meter equals 154,000 centimeter per second. That each second pulses coming and returning to the transducer. So 154,000 centimeter divided by 2 is the 77 centimeter per second, only going from the transducer to the tissues. And we should divide this line to the bottom depth to find the PRF, pulse repetition frequency. So it is not wise. It doesn't make sense that about like 1 mile in the body, we divide that to the centimeters. So PRF is the division of total of like 1 mile, 1,050, 1,540 meter per second, and we divide it, and the repetition time is PRF. If the depth of the imaging is doubled, what will happen to the PRP? Remember, it is PRP, pulse repetition period. When we we increase depth, PRP increases, but PRF decreases. PRP times PRF equals 1 because they are reciprocal. PRP equals 1 divided by PRF. PRF equals 1 divided by PRF. So when we tell PRP times PRF, we can put instead of PRP 1 divided by PRF, and this PRF with this PRF goes, they divide is 1, and 1 times 1 is 1, or vice versa. We can put PRP times 1 divided by PRP. They goes and it is 1. It is very important point. PRP is 100 to 1,000 times larger or longer than pulse duration. It means only less than 0.1% of time we send pulses, and we are listening. The machine is listening, is off time for waiting for the reflectors come back. So PRP is 100 to 1,000 times longer than pulse duration. The other name for pulse duration is active time. So active time is too much less than pulse repetition period. Pulse repetition period is on time and off time, both of them. PRF of the 6 megahertz transducer is in comparison of PRF of the 3 megahertz transducer. Very important point here. 6 megahertz and 3 megahertz is the fundamental frequency. With changing depth, PRF, PRP, and duty factor, frame rate, temporal resolution, lateral resolution, they are changing, but the fundamental frequency doesn't change. It's a very important point. All the time we should think about that. And if we have, for example, we determined and we choose 5 centimeter depth for 6 megahertz and 5 centimeter for 3 megahertz with same depth, PRF for both of them are the same. But PRF depends on the depth, but This frequency don't depend on the depth. They don't change. Very important point. And but with changing depth, PRP, PRF, duty factor, lateral resolution, and temporal resolution all change with depth. It's important. Please pause this video and review more than one time. I promise 100% you can do the questions for this chapter. I wish the best for you and thank you for your patience.